Hi, and welcome to the first of our videos looking at chromatography. Some of these ideas we've already talked about in class, so let's start putting some of the technical vocabulary to these ideas and talking about how we explain what's going on. So with chromatography, there are three different types that we need to be aware of for Unit 4. That is paper chromatography, thin layer chromatography, and high performance liquid chromatography, HPLC. And we'll talk about column chromatography as a lead-in to HPLC. So in this video, we're going to look at paper and thin layer chromatography, and then the next video, we're going to talk about HPLC and the differences that we see with HPLC. All methods of chromatography have the same principles behind them and common features. This is important because you will see exam questions which ask, how does chromatography work? Or the question is essentially, explain how chromatography works. Every form of chromatography has a stationary phase, a solid or liquid substance coating a solid surface, so this does not move, it is immobile, it is stationary, and a mobile phase. This will be a gas or liquid that moves through the stationary phase. Okay, the analyte will be the mixture that we place into this system. So essentially what we're analyzing will be our analyte mixture. So one of the things that we want to talk about is affinity. So when an affinity has a high, if an analyte has a high affinity for the stationary phase, it will spend more time bonded to the stationary phase and be slowed down, versus an analyte with low affinity for the stationary phase or a high affinity for the mobile phase. This will spend more time in the mobile component of the system and therefore will travel more quickly through the system. This idea is based on what we refer to as adsorption and desorption events throughout the chromatography process. The sample will be applied to the stationary phase or introduced to the stationary phase, and it is opposed to two opposing influences. That is, the ability of the stationary phase to hold on to the sample components and move them, i.e. whether or not the substance will spend more time dissolved into or stuck to the stationary phase, an adsorption event, or the ability of the mobile phase to carry the sample components through solubility or other attraction. This is desorption. So this is when it is not being stuck to the stationary phase. So as the mixture being analysed is swept along by the mobile phase, some components will stick more to the stationary phase than others. Ones that stick more are slowed down. Okay, they adsorb more strongly and they desorb less often. Okay, which means that they will be slowed down and travel less quickly through this stationary phase. The rate of movement of each component depends on how strongly it absorbs to the stationary phase and how readily it dissolves into the mobile phase. This is, of course, determined by the strength of intermolecular forces and the type of stationary and mobile phase that we are using. For paper chromatography, this is the simplest and cheapest form of chromatography. We have a strip of filter paper placed in a sealed container with a solvent. Okay, so this is our solvent here, which is going to form our mobile phase. Paper is our stationary phase. It is placed inside a sealed container to avoid evaporation of volatile solvents, which is often the case when dealing with polar solvents. The origin is marked, and this is where the mixture tested is to be placed. We mark this with a graphite line so it won't interact with the solvent, and then the sample is run by allowing the solvent to move up the paper using capillary action. When we place the paper into the solvent, it's important that the solvent does not cover the origin where the mixture is placed, or the sample will just be washed into the solvent and we will not get it moving through the paper. The next thing that we need to do once we have resolved the chromatogram is we remove the paper from the solvent and we draw a line where the solvent got up to. This is the solvent front. This is the furthest point that the solvent got to, so this is the most mobile of that component. Okay, then the components, if it has been a well-resolved chromatogram, will appear as single dots with no streaking, and we can calculate the RF for each dot by measuring to the center of the dot to the origin. We then take this value and divide it by the origin to the solvent front distance. Okay, this gives us a ratio that will always be less than 1 that can be used to characterize the components. The components that, if they are the same, will produce the same RF when run under the same conditions. Okay, remembering that these must be measured from the origin and not the bottom of the plate. This is a common error, so make sure you always double check where the origin, where the sample has been placed, the distance from this to the center of the dot, divided by the distance from the origin to the solvent front. RF values are constant and unique if the conditions that we run the TLC in, or the paper chromatogram, are kept identical. This is a typical kind of question that we would see for a TLC or paper chromatography question. A sample has been run, it has been found to find 3 components, and we are asked to calculate the RF based on this information. Quite often they may not provide these values for you and will expect you to use the ruler that you will of course have with you in the exam to calculate these values. So for each one, if we calculate the RF for component A, which is this one here, we are going to have 4.5 centimeters divided by origin to the solvent front, which is 6.4. And when we work out this ratio, we have 4.5 divided by 6.4, we get 0.70. These are 2 significant figures, so we want to give our answer in 2 significant figures. There is no units for the ratio. So the next type of chromatography that we see with this is actually thin layer chromatography. In this case, we're just using a more precise stationary phase. This is usually a glass or plastic coated sheet that is coated in adsorbent powder such as alumina or silica gel. These are the 2 most common stationary phases we see for TLC. The mobile phase will be an appropriate solvent depending on what properties we want to use. It should be able to easily dissolve the sample, and this will usually be a mixture of solvents such as alcohols or other organic solvents to tune the polarity between the mobile phase and the stationary phase. Typically, we will have the opposing polarity of the stationary phase in our mobile phase. So if we have a polar stationary phase, such as silica gel, we would use a non-polar mobile phase, such as maybe heptane or hexane organic liquid. This little video just gives an idea of how these dots are resolved using TLC. Okay, this is going to follow the same ideas as our paper chromatography. The mixture of products, okay, is in our sample. That sample is spotted onto the stationary phase. What we see here is our TLC tank or chamber, which is essentially a sealable jar. We have our solvent, which is our mobile phase, and our TLC plate, with our sample being spotted. The mobile phase is often referred to as the eluent, and it rises by capillary action up the plate, dragging the sample with it. The longer we allow it to run, the more resolved the spots are, because they have a greater time for which the adsorption and desorption events will occur, which increases separation. each spot will be a pure spot of that component of the mixture. So when we compare paper versus thin layer chromatography, paper is obviously cheaper and easier, but it can be slow. The capillary action up the paper can often not be as fast as what we see on TLC. It's also not as sensitive as TLC, and we can't resolve it in the same way. Sometimes with thin layer chromatography, we can't see the dots because they're not colored, but we can use things like UV light, which a lot of organic compounds will fluoresce under UV light. TLC over paper chromatography is it is faster, it has better resolution, i.e. the compounds separate better, giving us more compact dots. We see more streaking with paper chromatography. It is able to detect smaller amounts, and we can use corrosive materials that might otherwise react with the paper in a paper chromatogram. Neither method is able to separate complex mixtures that contain similar compounds because we won't get enough separation. There just simply isn't enough space for the absorption-desorption events that we need to happen in order to separate complex mixtures. Okay, that is it for paper and thin layer chromatography. Again, remembering that if we have a polar mobile phase, then polar compounds will move more quickly up the chromatogram, so the ones that would be closer to the solvent front would be polar. The less polar compounds will be closer to the origin because they will have a higher affinity for the stationary phase and not move as far. Next up, we'll talk about HPLC and how we can use instrumentation to make this process even more sensitive and reclaim our reactants.